Now let's talk about the memory system model. Okay. So this is one the component. Probably you have some ideas what it does. It stores the information. It stores data. And there are many types of memory systems. It can be read-only memory where you cannot write back anything. It can be like an read and write, so you can both read and write and retrieve the data. It can be that type of memory which retains the data even if you turn the power off. It can be that type of memory where information stored is wiped out as soon as you turn off the power or reset the memory or restart the system. So there can be many variation of it. Okay, but to understand the basic concept, we'll pick up one specific memory system model and stick to that. Okay, there can be many other type of operation, and it's an industry by itself. Memory is an industry by itself, and many companies produce different types of memories. It has different advantages, disadvantages, and so on and so forth. So we don't want to get into that details of the memory system and what's engineering specification and stuff like that. They're more suitable for computer engineering study. For our purpose, computer science purpose, to understand the computing system, we'll pick up a very simplistic model and we'll stick to that model. Even if it is simplistic, but it actually represent almost like I would say 70 to 75% categories of memory operation. Okay, so let's see what is there. Again, let's start with an API because we are software people and we are more familiar with the API concept. So that's why I start with an API. Okay, so this is an API which returns nothing, like a void. This returns nothing. Okay, and it takes three variable. Note there is a bracket missing there. Just correct yourself that there is a round braces just to syntactically correct. But anyway, the concept is that we are passing like three values, like a boolean read whether I want to read, and a write whether I want to write, and an index at which index I want to write. Just think and memory as a table. Okay, it has index of rows, right? 0, 1, 2, 3, 4, and so on and so forth. Large number. So you just specify at which row, which index of the row you want to write certain values. Now, here is a very interesting usage of a pass by reference variable, as I explained in the ALU module. What is a pass by reference? So if it is a read operation which is denoted by the boolean flag read as true and write as false, and in that case this memory subsystem will return a stored value in the memory into this variable. Now if it is a write, means your read flag is false, write flag is true. At the specific index, whatever value in this info variable, it will write back inside the memory. That's the memory as an API conceptually. Okay, and what is the simplest implementation? Like in a C, let's see. Let's say it contains like 1024 integer, just a very small memory. It is basically your one key information storage, which is, if we say one integer is 32-bit system, it is a 4 byte. So I'm talking about a 4 kilobyte data storage here in this case. Okay, so we defining a static memory, a static variable as a mem, which has 1024 indices. At each index it stores one 32-bit integer. Okay, so we pass the index. So what we do first, do a modulus operation, with respect to 1024 to make sure that the array index you are accessing is bounded within 0 to 1023. Right, this is just an measure for not to go into some crazy bug where my client whoever application writer passed an index which is value more than 1024. You see, this is integer. Integer can actually represent more than, way more than 1024. Okay, so that's an basically an preventive measurement for me to bound the array index within 0 to 1023. Okay, nothing more, nothing less. So now it is a simple code. If it is a read operation, then you access that array at that index and get the result into your info variable, or return it back basically to your application. Else, if it is not read and it is write, so our application is trying to write some values or store some values in the memory. So I update the memory content, that array content, with that info passed to me. Otherwise, no operation. Okay, if you not read, not write, it's a no operation. Read and write, no operation, we just return. All right. So this is the functionality as a very simplistic memory system model. Hopefully this is very understandable by you, because it's all nothing but some array you can think of, and in fact these arrays are stored inside the memory. You can think any memory as an array and vice versa. Okay, so how we represent as this guy as an interface diagram? It's very simple. We have, there's a memory of 1K. We just make a text tag of the box just to say this is a memory of 1K. And I have a read 1-bit signal, because Boolean is just to represent true or false. So just 1 bit is just needed, 0 or 1. 0 is false, 1 is true. So 1-bit signal to read, 1-bit signal write, and there is the index is a 10-bit, because I am trying to access 1024 location, 1024 rows in a table where I want to store values. So basically it can be represented by just 10 bits. You don't need more than 10 bits for that. Now here is an interesting symbol. So you see this symbol is like arrow in the both direction. This basically means this group of 32-bit signal used as both input and output. So it is an IO type of signal. It's an IO type of signal. Okay. So if it is a read operation, then this memory will write it out. Means it will send the content out into the whoever is calling for the asking for the data. It will just write it out. Now for the write operation, this acts as an input signal. Means at this index value, whatever value is set into this group of signal by the application or whoever is using this memory, it will pick up the value and store inside the memory. So that's the hardware. So we don't need to know what is inside this. We just are interested to know what things it does. Okay, what are the operations? So this is the interface diagram. Now the next will be starting about the timing diagram, which is very, very critical to understand the exact functionality in the temporal domain, okay, of a memory. So let's recap and simplify this interface diagram a little bit without the thick arrow. So I have read, write, address of 10-bit, which is input signal, and we have an input output signal, which is treated as a data group of data signal, which is 32-bit, and later we'll say that this is called a bus. Okay, a group of signal is always called a bus. This is an address bus, this is a data bus, this is a group of signals. There are two extra signals that I haven't shown you in the last slide, which is reset and clock. Okay, so a memory as a system, okay, it needs a clock. It always operates with respect to clock signals. And there is a reset signal upon which, let's say for this memory, if it is set to 1, all the content of the memory becomes 0. Okay, if you think of a memory as a table with rows, multiple rows, and each row containing some values, storing some values, if reset is set to 1, all the rows become 0. Okay, so that's the function of the reset. Normally, when we draw the complex diagram interacting between memory, ALUs, and other subsystem, we usually leave this reset and clock out because we know it is there. Its reset signal is connected to everything. Clock signal is connected to everything. Okay, but for this slide, we'll try to see what's going on in the memory. And another difference, just to note, in the previous clock subsystem module, I have shown you the clock signal as a trapezoid to represent near realistic signal, how the clock signal looks like. Okay, believe me, like in the real life, clock signal looks much worse. Okay, it's not very clean like that. Okay, even it is not like a trapezoid, but for most of the purposes, we can assume this is a square waves, what we call a rectangular wave, where there is no transition time between 0 to 1 or 1 to 0. From what we are assuming, your rise time is 0 and fall time is 0, and that's what gives you a square or rectangular signal. That's what we usually draw. Okay, but underlying concept is always there. There is a rise time, there is a fall time. This signal this cleanly goes up and down. It doesn't happen. Okay, but for the simplicity of diagram drawing, we assume it's in rectangular or square waves. Okay, and thus for the other signals too, except for the buses and group of signals, where to represent is always better to represent with a trapezoid or hexagon. Sorry, not a trapezoid, hexagon. So that it can visually represent it's a group of signal. Okay, but 1 bit, it's always a square waves and rectangular waves. So we have time points T1, T2, T3, T4, T5, T6, and at the T1 reset goes up, and then it comes down at T2 time. Okay, and this is the clock signal. T1, T2 is defined by this, or at least represented by this clock signal. And then, so in this cycle, which is called a reset cycle, all the memory previous contents is just wiped out. Okay, and then at the T2, I issued a read high and write stays to low. That means it's a read operation I'm requesting, and I'm also providing an address. So now here, one side thing to know is, look at this, like I didn't represent the value of this address pass between T1 and T2 with another trapezoid, because in this diagram it is not important. Okay, so we just represent as a dashed line, single line, and then when it is relevant, we just show the value. Okay, I have a bunch of signal values like a 0 cross 00A, for example. This is just an arbitrary example. So what it is all saying, between T2 and T3, I have set the address, I have set the read signal to true, and I kept the write signal to 0 or false. Okay, this is my read operation I specified. Now if you look at the diagram, I kind of include T4 till T4 as my read cycle. So why? Okay, remember, this is a physical system. It does not produce the data as soon as you give you its specification or as soon as you give you the request. Okay, it takes a time. So let's say for this memory, it is an treaty between this memory and the rest of the subsystem of the computer, is that it will take one clock cycle to produce a result. Okay, it will take 1 clock cycle to produce a result. Means when this request is presented, okay, it will definitely produce the result after 1 clock cycle. So this your request has placed in T2 to T3 this cycle. Your result or data will come out from the memory from T3 at the 3 time. It will be there, and you can use it for the entire clock cycle. Okay, so what it will do is basically your rest of the world can go and pick up the read value between T3 and T4. Okay, it can read it here. Most of the time it is being read here because that's where it is kind of like stable, more stable. Some subsystem picks up at this falling edge. Okay, so they're more advanced digital subsystem which basically takes advantage of the falling edge as well. But the basic point is that this data being read between T3 and T4, and no one better disturb this data. I'll say what I mean by data in a couple of minutes. Okay, so point is this: we placed and request in a time t between T2 and T3, and we can expect the result of the read operation comes out in the next clock cycle. That is what the treaty between this memory and the rest of the system, that it will take 1 clock cycle to generate the data or read the data out. Okay, and that's why this read cycle is from T2 to T4. And after that, I have requested at the T4 cycle, my write signal goes to a high or logic 1 and read signal is kept to 0. So during that cycle, I presented a address 00B for example, and also I give a data. Okay, I'm sending a data into the memory through this data bus of a value 1 to EF. So what will happen during this cycle between T4 and T5, memory will write this value into this index, into the table of rows, into that index, it will write that value. Okay, so in this case there is no one additional cycle, because this one says that I will complete this operation within the same cycle. I won't take one extra clock cycle there. It's the same cycle. Okay, so it takes the same cycle. During the same cycle, it completes the operation and it's done. Okay, now to observation point is that when I said that when during the read operation, don't better mess up with the data when memory is reading out or giving out some result. What does it mean? Here it is. Say I want to initiate this write operation between T3 and T4. Just imagine that. Okay, so what I need to do, I need to make the write signal high here, address here, no problem, because I don't care about this address value, so I can present the address bus with this address at this point, and then I need to supply the data into the memory. Now see, in this memory module I have only one data bus to either I get the result out or put the data in. So now imagine you are as a client, you are trying to write this data during T3 and T4 while the memory is supposed to get the data out during this time. So you are trying to write on this data. Memory is also trying to write on this data bus at the same time. if you initiate a write cycle between T3 and T4. That's a problem, right? You cannot do that. Why you cannot do that? Because there is only one physical data bus. Like these are the electrical signals, 32 electrical signals, and both memory and its client is trying to write onto this. So it will become error, right? It will become become a fight between these two components. Who is writing what, and your data will definitely be contaminated. Okay, so that's why you cannot initiate a write immediately after a read. You need to wait. Okay, so write after read is not possible. Like means write immediately after read operation request is not possible. You need to wait for another signal, if assuming your memory subsystem takes one more clock cycle to complete its operation. All right. So now let's look at the other combination. How about I am writing at this T4 T5? Can I initiate a read between T5 and T6? Yes, of course I can initiate that read, because I'm done with the write operation within one clock cycle, T4 to T5. So I'm free to make it a read operation here, making this read signal to high, keep the write signal to low, presenting one new address here, and that read operation will followed by between T6 and T7 the data will be presented at this cycle from the memory. So that means essentially I can do a read operation, request, immediately follow and write operation. How about write? Is the same simple thing, right? I'll keep the write high, keep the read low. I'll present possibly a new address or no, doesn't matter. I'll possibly produce a new data or no, it doesn't matter, but I'll give some data. I have no problem there, right? How about read and read? Let's say I request a read here. Can I request another read here? Answer is yes, we can do that. Why? Because there is a request, if there is a request between T3 and T4 during this time, making the read signal high, keeping the write signal low, presenting a address here, that corresponding read information will come out between T4 and T5. So a read request between T2 and T3 and another read request between T3 and T4 won't conflict with each other, right? Your result of the read operation between T2 T3 coming in T3 T4 and result of a read operation between T3 and T4 will come at T4 and T5, right? So read after read is possible, write after write is possible, read after write is possible, but there is a hold if it is a write after a read. You need to make sure you consume the read data and your read operation is completely done. Okay, that's the very interesting and very important concept you need to grasp.